Good afternoon. Welcome to the 24th Annual The Science of Consciousness Conference here in San Diego. Thank you all for being here. We have a lot of people to thank, but we're going to do it briefly, and if I forget, we'll add them during the week. First of all, I personally, and we all want to thank Abby Behar Montefiore. Wonder Woman is very popular in the movie theater, but she's the real Wonder Woman of this conference. We want to thank our sponsors who are listed here. University of Michigan, the Penrose Institute, the Manny Baumick Foundation at UCLA, Gratitude America, Quantum Gravity Research, the Arthur C. Clarke Center, Alvin J. Clarke Foundation, DEI. Okay, Jay Sanguinetti's lab at University of New Mexico. Anyway, thank you all. Thanks to all the sponsors. And thank you all for being here, because that's what makes it run. And I want to thank the program committee, James Tagg, Eric Vieri, Abby, Betsy Bigby, Jay Sanguinetti, and Pavel Pilkinen. We put together what I think is an excellent program. So without further ado, I'm going to introduce my friend and colleague, James Tagg, who is an artificial intelligence expert, entrepreneur, and general good guy, who will introduce the speakers for the first session. James.
Hi, so welcome to sunny San Diego and TSC 2017. I can assure you it does get sunny here, and in fact, that we were all in bikinis on December the 15th. And now I put a really horrible image into your heads, haven't I? No, not me, right? Not me. Anyway, so I think we live in very exciting times for this discussion of sort of consciousness and AI, because we're getting to the point where computers are getting more powerful enough that they can start to maybe pass the Turing test and give us some run for money as human beings. Some people find that a bit scary. Some people find it very exciting, and it will change everyone's lives. It will certainly change everyone's lives. Let's hope all for the better. Generally, scientific change has improved our lives over the years and not been a disadvantage. So I think many of the sort of the very negative things that we see, mainly coming out of Hollywood, are sort of a bit too negative. So we have three speakers today. The first one is Roger Penrose. Roger Penrose got Stuart and I both interested in consciousness many years ago when he wrote his book, The Emperor's New Mind. And Roger is going to explain to us how he thinks that humans have a different type of intelligence than machines, and that maybe it's a quantum gravity computer. Our second speaker is Joscha Bach. He thinks that computers indeed could be conscious, and sees no reason why not, and indeed will explain to us the theory by which they would achieve that sort of consciousness. And our third speaker is Hartmut Neven from Google, and he is building the world's most powerful computers, or at least they hopefully will be the most powerful computers in a few years' time when he perfects all of the things. So quantum computers, not the quantum gravity computers that Roger is saying that we need, but at least quantum computers. And he's going to explain to us how quantum computers work and how far they've got with building a quantum computer. Very fascinating talk and a very fascinating guy. So I won't talk any further because I'll use up valuable real speaker time. Let's have Roger Penrose up to the stand for this first speech. Thank you very much. Thank you.
Well, it's a great pleasure and an honor for me to be able to address this meeting, and I want to present the point of view that I've had for some while, although modified in various ways, which is that consciousness is not the result of computation, it's something else. Let's see if I can get this thing to work here. This old-fashioned technique, I'm afraid. I can't read what I've written, unfortunately, because my eyesight has deteriorated somewhat, but I hope you can. I can get the gist of what I said, and that is, well, consciousness, there are many aspects to consciousness, and people often refer to many of them like things that we feel, which might be pain, or which might be the appreciation of beauty, or love, or a color, or something like that, and the experience that we have. However, what I want to say is something very, very specific, And the argument is that if this very specific thing is something that can be shown to be not a computational thing, then this raises the question of whether these other qualities could ever be explained. In fact, it's more improbable in a way that the perception of the color blue, for example, is a computation than the things I'm going to talk about, because I will talk about mathematical things, and people tend to think mathematical things, oh, well, that must be computational. So I want to try and explain why that's not the case, and why understanding. I want to concentrate on understanding. I mean, of course, as I say, that is a very limited aspect, if you like, of what consciousness is, because we can be conscious of all sorts of things without understanding them. But understanding, I claim, is something which is demonstrably not the result of a computation. Of course, even in the way we use computers, the way we use computers is to do complicated calculations. The computer doesn't know what it's doing. It doesn't understand anything that it's doing. And I can illustrate that a bit more in what I want to say in a moment. But we have to present the understanding which tells us what computation to do and what the computation means in the end. So from that point of view, it's something rather different. Now, I'm not sure I can see, that's the trouble with this system, I can't see what I'm doing here. Let me move this so I hope you can see the whole transparency. I think you can. Okay, I think perhaps I've covered what's on that, so let me move on. Let me give you an example. This is one I made up recently. It's a chess position, and it's an example which is stimulated by an example which was made up a long time ago. But let me give you this one. So long as you understand the rules of chess, you will see this is a rather strange position. Black has an enormous advantage. You see queens and rooks and bishops and things. You might worry about all those bishops being on the same color. It's not an illegal position because two of the bishops were bishoped by pawns. You see, you can move the pawn up to the end and change them into a bishop. That's perfectly legal. And they're also on the same color, which you might worry about that, but that's perfectly legal again. So the position is a genuine one, and it's easy to see that it's a draw, because the black pieces here are all trapped by the barriers of pawns. They can't move if white leaves them alone. They're completely trapped, and the bishops can't do anything because the barrier is impervious to the bishops. They're on the wrong color. So it's obvious, if you know much about chess, that this can't be won by black. But if you show this to any of these very high-powered chess-playing computers, these will say that it's a win for black, and that you can see it's completely wrong. In fact, I think some of these will actually, because there's a rule about a draw, if you go on and on and on without a piece being taken or a pawn moved, and if you do that for 50 moves, then it's announced as a draw. Now, the thing is here that what black may, according to one of these chess-playing machines, the black starts sacrificing these bishops, which is ridiculous to do, of course, because it thinks that it doesn't want to draw because it's a win, you see, but it's not. And so all you have to do is move the king up to here, and then you checkmate in a couple of moves. So that's a stupid thing to do. So what I'm saying is that the little bit of understanding of what the game is about can get this particular position right, even though what's going wrong now? Okay. Anyway, it just shows that a little bit of understanding in certain circumstances it can defeat what a very, very powerful computer can do, which could defeat almost defeat or at least draw with any human. So let me move on. This is just to demonstrate that there's something a bit different about human understanding and simply computing. Of course, you could put rules like that into your program and make the right answer for those positions. But that's being wise after the event. Now, of course, you could argue that chess is a finite game, and so no matter how clever your position is, if you had a powerful enough computer, it could simply work the whole thing out to the end. This isn't a very good system, is it? Can this be made more horizontal or not? Yeah, that's better, thank you. Right. Just leave that down there. Oh, okay. Anyway, so what about the infinite? And this is where you start to see real differences. Now, you might say we can't think about infinity. That's completely wrong. For example, you could think about the statement, if you add two odd numbers together, you always get an even number. Now, that's a statement about an infinite number of things, and it's very, very easy to appreciate. You don't have to think very hard to realize that's true for all numbers, and for all numbers, that's an infinite number of numbers. So in mathematics, there's no real problem about thinking about infinity. However, the rules that you use to talk about infinity, that's where you can raise the question about the difference between understanding and pure computation. Again, I can't see what I've written here, so let's not worry. I hope it's on there, whatever I want to say. Now, let me explain how one often deals with the infinite in mathematics. Actually, some of these I may need back again, so I'm not quite sure what to do. Here we go. This is one of the ways that one learns at school about how to deal with the infinite. Suppose you had a proposition which depends on a natural number. When I say a natural number, I mean 0, 1, 2, 3, 4, a whole number, a non-negative whole number. Now, if you want to have a proposition which depends on a number n, a natural number n, how would you prove that that's true without running through all possible n's? Well, the standard way of doing it is to prove it's true for 0, and then prove that if it's true for n, then it's true for n plus 1. For some particular n, then it's true for that particular n plus 1. And that is what's called mathematical induction. Now, that's an example of something you could put on a computer. So you could put that rule on a computer. That's fine. And you could put all sorts of other rules on a computer. What I want to show is that rules actually, can I keep that one there, or is it going to flop off like the others? There's a very famous theorem, and my position on this was very much influenced when I was a graduate student at Cambridge, and I went to various things which weren't at all what I was doing. One of them was a course on mathematical logic, and I learnt about the Gödel theorem, and I'd previously thought, well, the Gödel theorem says you can't prove certain things in mathematics, and I didn't like that idea. But that's not what it says. So what it says is described here, and again, I'm afraid I can't read it, but never mind. Is if you're given a system of theorem-proving rules. Let's talk about theorems in mathematics about natural numbers. They could be things like Fermat's last theorem that Andrew Wiles proved a few years ago, or it could be the Gold-Bach conjecture, which is still unproved. That is that every even number greater than 2 is the sum of two prime numbers. A very simple thing to state, but nobody knows for sure if it's true. It probably is true, but nobody has a proof of it. But the way you could prove these things is have a system of definite rules. And these rules would give you a proof. Now, I'm calling the rules R, and the thing is that if you want to use the rules, you've got to believe that the rules don't give you nonsense, like 2 equals 3. That, of course, would be an example of an inconsistency. Now, the famous Gödel theorem, what Gödel showed, was that if you have rules which are checkable by a computer, so that is to say, if you have what you claim to be a correct application of these rules, and a computer can then check to see if that's true or not. So that's the kind of rules I'm talking about. So I should have said that this is not just Gödel's theorem, but it's the Turing version of Gödel's theorem. I think I want you to hold these things too, if you could. So let me see if I can find this. Yeah, hold all that. Thank you.
It's Turing's version.
Yes, so this is the Turing version of Gödel's theorem, which is actually a lot easier to prove than the original Gödel theorem. The Gödel theorem is horrible to prove. But the point about this, no, don't take it away. The point about this, is it in the right place?
I'll fix it.
Oh, it's not in the right place. Oh, it should be in the right place. It should be lined up right. Okay, thank you. Yeah. So what Gödel shows is that for any system of computational rules of proof, you can construct a particular statement about numbers, and this is what I call G of R, the Gödel statement of R, which has the strange property that, first of all, it's true, and secondly, it is not derivable by means of the rules. Now, how do you know it's true? Well, because it states something about the rules that you have to trust if you're going to use the rules. Now, you see, the rules, if you're going to use them and believe the results, you've got to believe that the rules only give you truths and don't enable you to prove 2 equals 3. So those rules have to be, well, they have to be consistent. If they were inconsistent, then you could prove 2 equals 3. So they have to be consistent, and let's say they have to be sound, which is the word logicians use for, they have to give you only right results. So as long as you have that faith in the rules, if you're allowed to use the rules and believe that using them gives you the right answer, then you must know that G of R is true. However, it's not derivable using the rules. So it's your understanding of why the rules work allows you to transcend the rules. So the rules, whatever they are, aren't good enough to prove G of R, yet your understanding of what the rules do does tell you that G of R is true. So we've somehow transcended the rules by our use of understanding. And now an interesting point here is you've got to understand what G of R means. And meaning is an essential feature here. See, what people don't think is, well, what's meaning? You just use the rules and it doesn't matter. And often in mathematics, you have systems where you're not interested in what the symbols mean, you're just interested in the rules. That's fine. That gives you a useful kind of area like group theory and things like that. But for this particular case, you really need to know what the elements that the rules are operating on are. And what these elements are natural numbers, 0, 1, 2, 3, 4, etc. And there are other systems where you have funny kind of numbers where the G of R wouldn't be true. So it really does depend on your understanding what the operations, what the things are you're operating on, what the things mean. And the meaning is something which is not encapsulated by the rules. And it's an important point that meaning is something different. Okay, well, what this basically tells you is that our understanding is not rule-driven. It's not a computational thing, but it's something we do in our heads, and it's something that enables us not just to do things like this, but to write computer programs and make them do what we want. And we know they do what we want because we understand what the operations are. So that's the way computers are used and so on. Well, I want to show you, see, what this tells me is that what is actually going on in our heads is not rule-driven. It's not algorithmic. There's something else. Now, you see, the laws of physics, I wasn't quite sure which order I would do this in. Let me do it here. I'm going to talk about, you see, I've just been talking about, maybe I'll take this. It's helpful, thank you. I've just been talking about mathematics, you see. And I said at the beginning that mathematical understanding is something very limited. You could understand lots of other things. What about understanding in general? Well, I'm saying if mathematics understanding, you might think this is the most likely to be something you put on a computer. But that's, on the other hand, it's the thing you clearly can't put on a computer. That's well-established piece of mathematics, that mathematics itself, there are many things in mathematics which are not computational. And I'll give you an example in just a minute. But what about other forms of consciousness? Well, conscious understanding, or what about consciousness? Human understanding is what I said. Human consciousness, animals. I would certainly believe that at least many animals have consciousness. I'm sure there are enough like us. People talk about their dogs and believe that they're conscious. I think it's absolutely right. Squirrels, I would think that birds are conscious, all sorts of things. But I don't know how far down it goes. What about life? Well, I think not all life is conscious, but there is a line between what's conscious and what isn't. And what I am saying, that conscious things are making use of something that unconscious things aren't. Do we have a problem? Okay. Now, I don't believe that our consciousness is some mystical thing which comes flying around and whatever it is. I think it is something to do with the way the laws of physics operate. Now, if the laws of physics are not computational, and I said I was going to give you an example. I think I put this slightly out of order from what I meant. I'll give you an example of something which is not computational. And these things are quite easy to, some examples are very easy to explain. I think this is one of the easiest ones, so let me say. Suppose you have a finite set of polyominoes. Now, what's a polyomino? It's, let me cover this up for the moment so as not to confuse the two. A polyomino is one of these shapes like one of these things. That is to say, a set of equal squares stuck together to make a shape. And the problem that we're trying to address here is, can you use that particular shape to cover the plane completely? If it's an individual square, obviously you could, or a little rectangle, clearly you could. But what about shapes like these? Well, individually, none of them would, but you might have a set of such shapes. Will that set of shapes tile the plane? Well, in this case, it will. And here, I've given you an example of how it's done. Now, you might say that it would be a nice computational issue to decide whether they could tile the plane or not. And in fact, if it were true that to tile the plane, they would have to do it in a periodic way. That is to say that you form some arrangement with those shapes, and that arrangement repeats and repeats and repeats and repeats in all directions. That would be a tiling of the plane, and then that would give you an answer that would tile the plane. Now, if that was the only way you could do it, then you could make a computer decide yes or no whether a set of shapes will tile the plane. But this is an example where that's not true. If you look at it, you will, I hope you can see it, it doesn't look as though it repeats. It sort of almost repeats, but it never does. And in fact, you can't tile with these shapes and make a repeating pattern. You can only do it by a non-repeating pattern. And that's a central feature of the fact that this polyomino problem, tiling problem, these things are called polyominoes if I didn't say that before. The polyomino tiling problem is not computable. It's just a nice example of such a thing. So you can have them, and you could imagine laws of physics which were based on the tiling of a plane or something like that. That's not the laws of physics we know, but that would be the sort of thing it could be. Now, I think it's at the bottom of this one here, if you can see what's going on. What are the laws of physics as we understand them today? Well, there's Newtonian mechanics. I should make a point here that starting with Newtonian mechanics, the laws that we know depend on continuous parameters. They're not just discrete numbers. So that's a little point one has to worry about. And I worry about it sometimes, but I'm not going to worry about it here. I think it's not the central point. It could have been. I don't think it is. You can certainly approximate Newtonian laws very closely by discrete elements. That's not quite answering the question, but at least it's an indication that continuous numbers aren't something which are going to make the story different. Okay, Newtonian mechanics. What about Maxwellian electromagnetic waves, electromagnetism? Add that to Newtonian mechanics. What about relativity theory? Add general relativity theory to it. Quantum mechanics. Do they make any difference? Are they things you could put on a computer? Well, people put these things on a computer all the time. So you might say, yes, they're computational. However, there is a little problem with quantum mechanics. A little problem, well, I'm going to say it's a big problem. Let me say, I'm afraid that I have to describe what quantum mechanics is, and that's not so easy. But let me give you a rapid description of the central points. And here at the top, I have an example of two experiments, idealized experiments, where you might have a laser here emitting individual photons. And here we have a mirror. Well, it's a half-silvered mirror, what's called a beam splitter. So that this photon, see, a beam splitter, half the light gets through, half the light is reflected. So what happens then? Well, you might say that half the number of photons get through and half of them are reflected, and we have detectors here and here. This one or this one will receive the photon, not both, not neither. And that's a particle nature of the photon being illustrated. It's behaving just like a particle. But suppose I have ordinary mirrors here and here, and another beam splitter, and I put detectors here and here. Remarkably, you find that these two routes that it might take cancel out as going upwards, and they all come this way. And that wouldn't work for individual particles, because if you had a single particle, it might go this way and this way. This one, it might go this way and this way. That means half of them will come this way, half of them will go that way. That's not true. They all go this way. And you can only understand that, really, if you think of it as a little wave, and these waves cancel each other out when they come this way, and they add up going this way. So that's the way we think about quantum mechanics. But let me say a little bit more. The way we think about quantum mechanics, you see, this is just individual particles. But here, you see, these have these different routes. And what you want to say is that the photon takes this route, and it sort of takes this route at the same time. So it does two things at once. And that's the way we think about quantum mechanics. Particles can be in two places at once. It's a crazy thought, but that crazy thought seems to be true of the way individual particles behave. And the way we think of that in quantum mechanics is that you sort of add together the two possibilities. It could do one thing, plus it could do the other thing. So your combined state is adding the two things together. And we don't just add them together, we add them together with complex numbers. A complex number is a thing with square root of -1. Don't worry about the details here. I just want to give you the general picture so that you have these weighting factors, which are these funny numbers. You need them to do that to make the interference work and everything. But let's not worry about the details. Now this, I've used the letter U here. What does that mean? That's the Schrödinger equation, the evolution according to quantum mechanics. And the thing I want to say is that it's what's called linear. That is to say, if you have a superposition of one thing and another thing, and if one of the things would do such and such according to the equations, and if the other would do such and such according to the equations, then the superposition of the two together will be the superposition of the two results. I'll say a little bit more about that in a minute. That's what unitary evolution, or the Schrödinger equation, says. That's half of quantum mechanics. The other half is what's called making a measurement, or the reduction of the quantum state. And that's a little paradox, because quantum mechanics is a paradox with itself. It's sort of self-inconsistent. People don't usually emphasize that point. The thing is that when you make a measurement, you then say, oh, well, this superposition of two things, one of them happens or the other, and the probabilities are given by these, with a squared modulus of these complex numbers. And that's what's called R. That's the reduction of the state. That's what the thing does when you make a measurement. Now, let me go on, because I can't remember what I said at the bottom of that slide. I want to give you an illustration, leave that there, a little illustration of what quantum mechanics linearity means. Now here we have, I think I'll start with this one here. Here we have an example. There's a laser emitting, can you see that there's things which should be off screen and they're not. Here's a laser which emits an individual photon, and if it goes this way, it hits the brown thing and it produces a whole lot of junk. Okay, that's one thing it might do. Suppose we put a mirror in the way, then it's reflected off the mirror, hits the green thing and produces a lot of junk. Now what quantum mechanics says is, suppose we make this a beam splitter, so it's a half silvered mirror, half the light goes through and half the light is reflected. Then whatever this does produces this junk, whatever that does produces that junk. Both these things happen together in superposition. Well, that's the way it works. Looks strange, but that's the way it works. I'll make it look even stranger in a minute, because here is an example, a sort of example that Schrödinger himself was like to do. Here we have a poor cat, which is, here's the laser again, which hits this detector, and that fires the gun and kills the cat. Now, if I have it the right one, yes, that's the right one, kills the cat. Suppose there was a mirror there, then it reflects off the mirror and the cat's alive. But suppose it was a beam splitter. Of course, that's the problem. If it's a beam splitter, then the cat is alive and dead at the same time. And Schrödinger was saying that's a load of rubbish. You see, people sometimes quote Schrödinger's cat and say, well, Schrödinger said you could have a cat which is alive and dead at the same time. What he's more saying was, no, It's just showing a weakness in our understanding of quantum mechanics. Because if you follow his equation, because it has this linear property, that means that you have to, if this beam splitter says this and this happen together, that carries right up to the level of a cat. Often people say, oh, well, that's not enough. You should worry about the environment. You should worry about the observer coming along and all that kind of stuff. Okay, well, let's worry about them to some degree. And here we have an observer, and we have an atmosphere, and here we have the mirror thing being reflected, and what happens with the beam splitter? Well, it doesn't help. It doesn't matter whether the environment's there or not. It doesn't matter whether somebody comes and looking at the cat. You might, here's the cat, the person looking at the cat, and of course I don't know whether you can see the difference. One has a smiling expression and the other frowning expression. And the point is that the observer seems to be in a state of confusion about seeing a live cat and a dead cat at the same time. And you might say, well, how do we know what the thought processes of the observer are? Do they satisfy quantum mechanics or something? And, well, you just look at the expression. You see that's a superposition. So there's something funny, something going wrong. Well, many people take different views on this. And one of the common views is that you have to take both of them at once, and it goes right the way up. And there are two worlds, and the cat is alive in one world and dead in the other world, and if you come and look at it, then you're in a world, whichever it is, and so on. It doesn't quite make sense, because you've got to have a world which involves, or you should have a multiverse or something where all these different things are happening. And we really want a theory which describes the world we perceive. We don't want a theory which describes all sorts of worlds we don't perceive. So it seems to me, or a world which is some kind of superposition of all these worlds. So we really need something else. Now, my own view on this is that what we need is something to do with gravity. Now, people often say gravity, well, that's ridiculously tiny. How is the effect of gravity going to make the slightest difference to most of these things? It's an incredibly weak force. That's a correct statement, but it's not a relevant argument, because the way gravity comes in is just in changing the way we look at things, not so much that its gravitational forces are relevant. It's not the forces at all. I want to remind people of the foundational fact of Einstein's general relativity, which goes back to Galileo, and you have to imagine Galileo dropping a big rock and a little rock from the Leaning Tower. Of course, he probably, maybe never did that. It may be apocryphal. Never mind. He certainly thought about such things. And let's imagine the big rock and the little rock dropping. They drop together, as we know. Forget the air resistance. That's secondary effect, not important here. The big rock and the little rock drop at the same speed. And if you were an insect sitting on one of the rocks looking at the other one, it would seem to hover as though there were no gravitational field. So you can get rid of gravity, at least locally, by falling freely. And this is now familiar. Space travelers can be floating around in space without feeling the field of the Earth, which is sitting right there. And that Earth's gravitational field is not felt by the astronaut at all, because the astronaut is falling freely. Falling can be around the Earth in an orbit, that's fine, and doesn't feel any gravitational force. Okay, that's the principle I want to use. Now, this is a detailed argument, which I'm not going to go through here. I just want to flash it at you. If you have a quantum mechanical experiment which involved gravitation, and let's suppose this is it sitting on the table here. So the Earth's gravitational field is supposed to be taken into consideration. Now, you could do it the Newtonian way, which would say gravity is just another force, and you do the usual thing that quantum mechanics people do. They do what's called putting a term in the Hamiltonian and so on. Don't worry about what that means if you don't. It doesn't matter. But there's a standard procedure that people use, and then gravity would be like everything else, and it wouldn't cause any problems with standard quantum mechanics. But if you take Einstein's view, it's the one I just showed you with the freely falling, gets rid of gravity, then you say gravity is really just the effect of an acceleration. I mean, it's just like an acceleration, so that you use a frame of reference which falls freely under gravity, and then the gravitational field is gone. Now, this gives you two ways of looking at your experiment. And they almost come out the same. If you go through the details, you find they almost come out the same, except there's a funny thing called a phase factor, And that funny phase factor has a rather irritating term which involves the time cubed. And that's a technical point. The point is, though, that it tells you the following, that if you were doing these two different ways of doing gravity, they give you what are called two different quantum field theories. And you can't stick with one or the other. It's fine here if you only got one gravitational field, you can stick with one or the other, and that's fine. But suppose you had a gravitational field of an object. You see, this is my Schrodinger's cat. A big object which has been displaced into two places, and its gravitational field is the thing we're going to worry about. Now, this one will have a different gravitational field from that one, and since the quantum field theory is different for this one from what it is for this one, this means you're not allowed to make these superpositions. And so the superpositions are not consistent if you take the Einsteinian view for gravity. So this tells you that there's a basic conflict between Einstein's general theory of relativity, beautifully, I should say, confirmed. Quantum mechanics has an enormous number of confirmations, but so also on quantum mechanics usually on a small scale in one sense or another. In the gravity, it's on a large scale in one sense or another. But you want these things to come together and make sense as a theory as a whole. And what we see is that they're fighting against each other. They don't live together in the way that we normally do quantum mechanics. So my view on this, the way to get out of this problem is that this R process, which I think have I 5 minutes, have I? This R process, which there's some trouble with this system, it's probably sitting there somewhere, which is the measurement part of quantum mechanics. You see, they've got Schrödinger equation, it chugs along until somebody makes a measurement. And then making the measurement, you violate the Schrödinger equation. Yes, it wasn't that one, sorry. Never mind. Let's not worry about it. It tells you, see, following the Schrödinger equation, you have these superpositions. So you say, this thing and this thing happen together. The rock is in this place and it's in this place at the same time. But the measurement part says, no, it's flopped to one or it's flopped to the other. And usually people say, well, somebody comes and looks at it. But I'm saying that's not the point at all. Because of what I was just saying, it happens spontaneously. It becomes one or the other. Now, that's not something that most quantum physicists will say. If you ask them, they'll go on to one of these other explanations, which I don't think work. But what I'm saying is that the correct answer is that it does spontaneously become one or the other. Now, I'll say a little bit more about that. In fact, what I was really going to say is probably not the one I have next. Yeah. I'm not even sure I have it. Never mind. You see, you can have experiments. There is currently an experiment which has been going on for about maybe a couple of decades, where you have a little tiny mirror, and this little tiny mirror is about a tenth of the thickness of a human hair. It's very, very tiny, just a little bit too small to see. And the idea is to put this little mirror into a superposition of two little slightly different places. And you can do this by hitting it with a photon, banging it 1,000,000 times with a photon, and that will be enough to displace it so that the nuclei in that little mirror are displaced a little bit away from what they were before. And you then work out a calculation from the argument that I just didn't show you, but carrying that argument to its conclusion, you deduce that this slight displacement between the two instances of that mirror will make it spontaneously become one or the other in, depending on details, seconds to minutes, something like that. This experiment is being done by Dirk Baumeister, and he's been working at it for a long time. I don't know when there will be a conclusion on that. I would be fascinated to see. And we want it to be a positive conclusion, in other words, that quantum mechanics is violated at that scale. And the scheme that Stuart Hameroff and I, the orchestrated objective reduction, does involve this idea. So I should say, when people say, isn't that scheme wild and crazy because it involves quantum mechanics in the warm, wet environment of the brain, I'm saying it's even crazier than that, because it's not that quantum mechanics has to be sustained in this warm, wet environment, and we believe it can be done in microtubules, things like that. That's the idea. That not only that you sustain this quantum coherence at that level, but that you can actually get it up to the level at which we need something new in quantum mechanics. Now, why am I talking about this reduction of the state and all that? Because this is the only place I can see where there could be a non-computable physics going on. And it's not, well, sometimes people say, well, here's a mystery and here's a mystery, they must be the same, and that's my argument, ha-ha. Well, it's not what I'm saying. I'm saying that the argument is that we need something which is different from conventional physical theory, but which is also a big enough effect that it could be relevant to what we're seeing. It's not that consciousness is some mysterious particle running around and we finally collect them in our heads or something like that. It's not that at all. It's that this process of the reduction of the state, and here is my last transparency, which I hope explains what I'm saying. This is a sort of space-time picture, and here we have a lump being put into a superposition of two places. Now, time is going this way, upwards here, and here we have a picture, you're supposed to think of that as space-time. And the gravitational field of this lump warps the space-time a bit, and you have this little channel which goes along, which follows the history of that lump. Now, if it's put into this superposition, you pull the two apart, and then you see these two channels deviating, and the space-times now don't fit together properly. Now, the argument is that in a space-time volume of order 1, in what are called Planck units. Now, you see, people who work in relativity theory and quantum mechanics know what Planck units are. They're completely stupid units from the ordinary point of view, but I've got them down in the picture here. I can't read them off, but maybe you can see them. The point is that in Planck units, Planck's constant over 2 pi, the reduced Planck's constant, is put equal to 1. The gravitational constant is put equal to 1, and the speed of light is put equal to 1. You just get away with doing that. That's perfectly all right. It's just crazy units, but nevertheless. But if you use those units, it's that the measure of the space-time splitting, how much volume is there in that, is of order 1 before one of them persists and the other one dies. So this is the idea. You have a universe with a lump in one place, then it's in 2 places superposed, and then one of these dies and the other one survives. Now, the point I'm making is that in current quantum mechanics, well, they don't even think about it this way, but in current quantum mechanics, this is a purely random process. What I'm saying is it's something much more subtle than that. It's something which is a non-computable process, but not necessarily, it looks random, but it's not necessarily random. And there's something which I'm referring to, Stuart and I refer to as a moment of proto-consciousness. So if you like, this is the building block in this scheme of what consciousness is made. So I'm not saying this is conscious because it's not got any meaning to it, it's not related to other things, it's just an element of what you need to build consciousness. So the argument is that whatever consciousness is, it's a physical thing, but it's not part of the way physicists normally think about physics. It's part of the extension to current quantum mechanics that I believe is necessary, and which I hope will be revealed in experiments, and that is the building block out of which consciousness is constructed. Of course, it's a real challenge to see how this idea can actually be playing a role in, well, we presume microtubules, maybe other structures in the brain as well, in an organized way, in an orchestrated way, such as this objective reduction, that's the OR of the OR, the orchestrated objective reduction can actually be playing a role, the role that consciousness does in fact play in the way we behave. Thank you very much.
Get this to work. Amazing. Okay. I think the last, or the best contribution of the last century to the sciences was the discovery of the concept of computation. Computation treats arbitrary systems as sets of discernible differences. The fancy name for discernible differences in science is information. And we can group these discernible differences in states and then can describe an arbitrary system by how these states change. And the way they change is usually described with some kind of transition function. And the description of a system using a transition function and states is the most general way to capture the notion of computation. Digital computation is a very special case. In digital computation, the states are discrete, and the rules for the state change are deterministic or probabilistic. We can use this language of description to describe any system that presents itself to an observer as a set of discernible differences. For instance, the universe, or the observer itself. So if we look at these different computers, what kind of computer would we need to run the universe? At the moment, we don't know that, but imagine I describe the universe as a set of discernible differences, observations that I can make, and how these change into the next state. And I would want to build a computer that can run our universe, and I want to buy the cheapest computer that I can get away with. What would I need to look at in order? The cheapest one I could buy is probably something like a very big computer like this one, just with much, much more memory. It's a finite state machine, discrete, and so on. Way more memory. Speed doesn't matter if you live inside of it, of course, because you won't notice if it's slow or fast when you are inside. It could be probabilistic, which means you can branch between the states with some probability function, or it could be a quantum computer in which each state can be a superposition of states. Or maybe this is not enough, and maybe we need something like the one of the three versions that I just mentioned with infinite amounts of memory. This is going to be infinitely more expensive, but it could get even worse. If it has infinite memory, number one, that's your Turing machine, as we know it from these usual definitions of computation. It could also be a geometric hypercomputer, which is what physicists believed for the longest time. That is, that the universe is something that is continuous and is able to perform continuous operations. It's something that you cannot do with a digital computer, can only approximate it with a digital one. Or it could be an acausal hypercomputer, one where you can take information and calculate it and send it back in time and use these observations which break causality in a closed time-like loop. That's also a computer, it's just one that is not, cannot be simulated on a discrete state machine. So, computation is the description of an arbitrary system as states and a transition function, and computationalism is the notion that computation is necessary and sufficient for describing all conceivable observables, including, of course, consciousness. By the way, number 1 and 2 are the only ones that we know how to build in this universe. And one of the speakers after me, Hartmut, is going to talk about that he's working on building number 3. And one of the speakers after me, James, is going to talk about that the universe is possibly an acausal hypercomputer. Roger's thesis is more radical. He says that there's something going on in the universe possibly that is not computational, that is cannot be described as states and transitions between states, something that is not afforded by current physics, so we would need to go beyond physics, and something that boggles the mind because it's very hard to imagine what that could be. What is not computational? Well, there is stuff that is not computational. For instance, most of mathematics. How can that be? Well, mathematics is not computation. Mathematics is the domain of all formal languages. It's the domain of specification languages. You can specify arbitrary things, most of which won't work, right? In language, you can say stuff that doesn't pan out. And most of mathematics is not computable, whereas computation is the domain of possible implementations. So computation itself can never run into a paradox or be impossible or anything like this. Computation is just what it is, a state, a transition function, then comes the next state, transition function comes the next state. That's it. So if we try to describe the universe, we do this with physics. If we try to describe minds as information processing systems, we can do this, for instance, using artificial intelligence. This was largely why this field was started in the 1950s, after people realized that psychology isn't going anywhere. Can AI reveal the nature of our minds? Current AI, probably not. Current AI is a strong movement which is called deep learning. It's super successful, and it actually started pretty much 5 years ago. 5 years ago, a group of engineers led by Andrew Ng from Stanford and Google built a neural network with 9 layers on 16,000 computer cores, and they showed it randomly selected frames from YouTube. 10 million of these frames. So order of magnitude more than a baby is going to see in the first months of its life. And after that, it was able to recognize this stuff from an image database with 15.8% recognition accuracy, which means you could show it an arbitrary picture and it could tell you in 16% of the cases what's on that picture. And it hadn't been trained to know what it was seeing on these YouTube frames. It was just looking for structure, for anything that makes is a discernible structure in there. And it got internet famous because one of these things it could recognize very well was cats. Which is not surprising when you remember that it was trained on YouTube frames. So deep learning is basically using stacked hierarchies of layers, and which are feature detectors, and it uses a method, largely gradient descent, to approximate functions that allows us to classify objects and learn policies. And this means that in 2015, these things outperformed humans in recognizing images in that database. They didn't stay at 16%. They really outperformed people at doing this. They also got better at, than people at playing Pac-Man, being trained from scratch and not being told what to do. In last year, they outperformed people at the game of Go. And maybe 2020, we will have the first self-driving cars. At the moment, they're already outperforming the average humans in driving a car, which we, for some reason, don't think is good enough because they sometimes make accidents, but on average, they make fewer accidents than people. And there is an argument to be made, if it's really about saving lives, we should switch right now. Of course, this is very far from a mind. And when you think about building artificial minds, we often think about the Turing test, a system that convinces people that it's intelligent. I don't think that is the actual challenge. The actual challenge is a system that performs a Turing test on us, right? It's what we do with each other. We talk to each other to find out what the other person is conscious of, right? We don't try to convince others just that I am intelligent. I already know that. I want to find out what you know. I want to find out what you think about, what you are aware of. And once a system does this with us, we can recognize that the system has an idea what it is, that it starts to become a mind, that it recognizes us as minds, that it makes models of the world in which minds figure prominently. How long does it take to get there? We don't really know. Marvin Minsky said, if I believed in realism, if we work really hard, we will get there in between 400 to 400 years. And we are pretty much on track, I think. But we could say that these systems that we need to build, cognitive AIs, are different from the narrow AIs that we have right now. The narrow AIs that we have are largely pattern recognizers and object classifiers. So for instance, if you want to get such a system to recognize Alyssa, one of the dancers in that image, it means that the system has to filter out everything in the image that is not Anna, that is a variant, to find the invariant. The invariant would be Alyssa. So it treats to filter out the pose, the lighting, the dress, the facial expression, and so on, until only Alyssa is left in all the images that contain her. But this is not quite what people do. What people do is they take all these different concepts and don't filter them out. There is no background. There is only partially occluded other objects and images, right? What we do is we create a whole world from what we look at. And we relate the features of that whole world with each other. And we do this starting from patterns, then we go to percepts, and then we go to mental simulations. And then we go to concepts, which are abstractions over these mental simulations, and then to linguistic symbols that allow us to synchronize our conceptual domains and, to some degree, our mental simulations. So minds are not classifiers, they are simulators and experiencers. And they start out with feedback loops because they are in the service of control of the needs of a social primate. Most of the feedback loops that we have are not available to our conscious interaction with them because they don't need to. For instance, we regulate our body temperature, our heart rate, our breathing patterns, and so on autonomously with a lot of feedback loops, many of which are in the brainstem. But for some of the things, we need to be able to control what we are doing and adapt our actions. And for that, we have pleasure and pain. They are residing in the limbic system largely, and pain tells us, please do less of what you're currently doing. Pleasure tells us, do more of what you're currently doing. And then we have impulses, and they are directed on future pleasure and pain. And we have a whole motivational system that gives us impulses, many of which are physiological, some are social, and a handful are cognitive. My own work is related with discovering these motivations and building computational models of them. To associate these motivations with situations in the world, many animals have a structure that is called a hippocampus that matches patterns in the environment with the needs of that organism. So it knows what impulses should lead to which world situations and which world situations it should try to get to. But of course, it's very difficult to make sense of the world if it's just a bunch of patterns. So we have something more than the hippocampus. We have the neocortex. And the neocortex allows us to generalize over situations, to say, for instance, what do all the restaurants have in common? How can I recognize all these situations where I can get food and so on? Or how can I recognize Alyssa in many, many situations? And to do this, our brain needs to do something very tricky. It needs to generalize. And a good metaphor to understand what it's doing is a synthesizer. If you ever played around with a synthesizer, it has a bunch of knobs and buttons, and you can twiddle these until the synthesizer makes exactly the sound you want. Now imagine you take that synthesizer and you connect it to the output of your cochlea. This is the organ in your ear that basically performs a hardware Fourier transform on sound waves, and this is then piped to the cortex, and the cortex takes these signals and it fiddles knobs and buttons until it's able to predict what signals are going to come next from the cochlea, which means it understands the current sound. And once it has done this for a number of sounds, it generalizes over those sounds and looks what do all these sounds have in common. So for instance, all these different sounds have one property that makes them different, and it's the pitch. Once you filter out the pitch, you recognize you can now take a whole class of different sounds and lump them into one function that makes it predictable. And then once you discovered the nature of pitch and the different sounds that you can generate it, you find another feature, for instance, loudness. And once you've done this, you get to the next level and you can build something like a sequencer, something that is able to assemble sounds into rhythms. And then you go a level above that and you can build harmonies and melodies and so on. You go a level above that, you can build songs, and you go a level above that, you can build musical styles, and so on. And then you can go across the modalities and do this for different modalities. You do the same things for color, for spatial frequencies, and so on. You take your synthesizers, plug them into high-level synthesizers, and you do this until you can create a whole mental simulation, a dream. Because this is what the world is to us. It's a dream. We don't live in the world out there. We live in the dream, in the simulation generated by our neocortex. The same circuitry that produces dreams at night produces dreams during the day, which gets loosely synchronized with our sensory input, right? I think most of us understand that we don't live in the world out there. The interesting thing to realize is there is no colors in the world out there, no sounds, no people. There's a weird quantum graph out there probably. We don't know what it is, but colors, sounds, people, and so on exist in our neocortex as mental representations that allow us to predict the next set of bits that is going to hit our retina. And above these mental simulations, we create concepts as abstractions over what elements in the simulations have in common. It's like the address space of our sensory motor scripts. And then on top of those, we can create linguistic symbols to talk about them and self-report and so on, control our self-reports. For this, we need different types of learning. One is function approximation, which is Bayesian, usually parallelizable, and it's exhaustive. So we use this, for instance, to learn the laws of perspective in the first months of our life. And then we have scripts and schemas, which are narratives, stories that we use to describe, for instance, what happens in a restaurant or what happens in the financial markets or in society or in politics. And this is largely what we are talking to each other, right? And we can use these conjunctions of those to direct our mental simulations. So this is what the neocortex is doing. It's simulating a dynamic world. And at the moment, we don't have all the elements for that in place in our machine learning models. I think the basic unit is probably not a neuron because it needs to be compositional. It needs to be able to rearrange in different things. The basic unit is probably a cortical column. We have something in the order of 100 million of those. And each of them is probably a state machine made from something like 100 to 400 neurons, which has a function approximator and combines it with different learning modes in different ways. It can link up to its environment. And these cortical columns are linked up into cortical areas. And these cortical areas are linked with each other into processing streams and form these hierarchies of synthesizers, so to speak. And together, there's something like an orchestra. We have something like roughly 50 brain areas that are made each from an order of 100 million of these units. And they talk to their neighborhood and they form processing streams, right? And starts out from sensory patterns and motor patterns and gets integrated into more and more abstract things. And there's also a conductor. And the conductor is not a homunculus. The conductor is not something that has superpowers or something. It's a brain area like others. In the same way as a conductor in orchestra is not a Superman, but he's similar to the musicians. He just has a different task. And the task of the conductor is very similar to the conductor in orchestra. Its task is to resolve conflicts and tell individual instruments to be a bit louder or a bit louder, or to make something slightly different, or to listen more to this guy to his other side, and so on. And the conductor is in this way controlling what's being played tonight. If you take the conductor away, the person becomes a sleepwalker. The sleepwalker can still do interesting things, like get up from bed, make dinner, open doors, walk on the street, answers questions in random ways, but there's nobody home. Nobody is able to integrate this with the motivation of a consistent agent and create a consistent protocol of what's happening and learn based on that protocol, right? So this is what this conductor is doing. It gives you attentional awareness and integrates experiences. And the brain is probably, it's all done largely by the dorsolateral prefrontal cortex and some neighboring areas that provide infrastructure for that. But the important thing is to realize, of course, you're not your brain. You are a story that your brain tells itself largely through the protocol of the conductor. So you have the sensory perception, you build distributed hierarchical representations from them, which are your mental simulations, and then you have your conductor that is able, in a secondary process, to scan part of these mental representations, to basically see what your brain has decoded from the world. And most of the stuff is done completely subconsciously, autonomously, in parallel in the background by your brain. Your conductor is really paying attention to only very few things there, and more largely not in real time. And on your model, you have your mental stage, world model, self-model, procedural memory, object memory, and so on. So all this is part of your world representation, including your model of yourself, of how you interact with the world, and the model of that model, which we usually call the self. Your conductor also keeps a protocol of what it attended to. And this protocol is the only place where experience is integrated. There's something like an equivalent of experiences in many parts of your brain in distributed fashions, but these different parts don't know about each other unless they talk to each other. And when you self-report or report to other people, you need to have an integrated place where this information comes from. This is exactly that protocol of what you attended to. You can only remember of what you attended to and put in that protocol. Right? You can also then use this protocol to get activation into it to recreate a mental simulation or a partial mental simulation that is very similar to the simulation that happened when you looked at a particular thing or were in a particular situation. So you can use this to recreate situations, you can recreate memories, you can recreate particular dreams and learn from them. And they're sufficiently similar to the situation that you had and that situation that you can learn from them. And then you can also put the fact that you accessed that protocol into your protocol, which means it now becomes somewhat recursive. Doesn't mean that you are truly recursive, you just become aware of the fact that you did access your protocol and this created a particular mental state inside of you. So basically you take the model of your own recall action that you model at some point in your mind, because it's part of your mental landscape, and put that into the protocol itself. So this conductor maintains an attention protocol, which is a narrative about the self, and it has access to the protocol, which gets integrated into the protocol itself. I think that remembering having been conscious of something is both necessary and sufficient for consciousness. That is, I don't need to be actually conscious of something. It's necessary that I remember having been conscious of something so I can report about it to myself and to others. The availability of my mental simulations to my conductor is necessary and sufficient, I think, for access consciousness. And the integration of the access into the accessible protocol is necessary and sufficient for my self-report about the awareness. And the self-report, in turn, about my memory of awareness is interpreted as my awareness in actuality. What does it mean? It means, for instance, if you are drinking a cup of coffee and you feel how the coffee goes down your throat, this is, of course, not what's actually happening. What's actually happening is that you have some sensory neurons in your throat, in your larynx and so on, that get stimulated by the coffee. And some of that information gets integrated and transmitted to your brain. And there it gives rise to a simulation in your somatosensory cortex, which happens something between, I think, 700 milliseconds and 1.5 seconds after the fact. And is totally different from what physically happened with the coffee in your throat, right? but you perceive it at the same time as which you subjectively take the cup and take it to your mouth, and you hear the clinking of the cup to your teeth, and so on. All these things happen simultaneously, even though the processing of the sound took a very different amount of time, and the processing of your movement took a very different amount of time, because they're very different sensory modalities with different mental representations. How is it possible that they subjectively happen at the same time? Because they are patched together in the protocol, and you only get access to them long after the fact. And they're patched together in the protocol in a way which they didn't happen together, which means you're not conscious in the right here, right now, when you drink that coffee. You're not aware of that coffee while you drink it. You're only aware of it a long time later. And when you actually navigate the cup, you do this with reactive subsystems that have been primed by previous conscious interactions, right? So I think that you're probably not conscious in actuality of things like that. You're probably having a memory of having conscious of something, of experiencing something that didn't take place in exactly the same way as you remember it. That's the easiest explanation of how to make a machine conscious, is to give it a memory of having been conscious of something. That's it from me.
Thank you. Good afternoon. And thanks to Stuart and the organizers for having me here. I want to present from work from the Google Artificial Intelligence Lab and tell you a little bit about our experiences in building actual quantum processors, and then maybe relaying some insights, some learnings from this effort to this community who is interested in whether quantum effects do play a role in higher brain function. And I will go from sort of more hard engineering to more speculative ideas. So first, I want to explain you an experiment that you may have read in the news about, and knock on wood, we hope to be able to perform it later this year. And this is the so-called quantum supremacy experiment. It's a bit unfortunate name, but it was given by the Feynman professor at Caltech, John Preskill, and then it was refined, for example, by Sergio on our team. But the basic idea of quantum supremacy is that you have a well-defined computational task, and you have a quantum processor that can do this task in a short time, say a second, while even the fastest classical supercomputers that would be currently Taiwan Light in China would not be able to do this in a reasonable time, let's say a year. Note, however, that for this benchmarking, it's not necessarily required that it's a useful task. It can be an exotic mathematical problem. So how do we perform this experiment? Of course, if you want to win with a quantum processor, it's maybe best to start on the home turf of the quantum processor, and you write down a quantum algorithm. And you may not be familiar with this notation here. The details don't matter so much. I often refer to it as quantum sheet music. It has three basic parts. You start your qubits in time 0. Let's say here I all started them in the 0 state. And then there's a bunch of gates that either act on a single qubit or on 2 qubits. And you apply a number of those gates, and then at the end of the day you will have a quantum state, and possibly it can be a superposition state that is sort of a very broad, entangled superposition over, if you had n qubits to start with, could have support over 2 to the n classical bit strings. So the Hilbert space involved here is 2 to the number of qubits you start with. And then you will, at the end, measure the state. But measuring a quantum state is really sampling from a probability distribution encoded in this quantum state. So the next thing you're going to do is you take your quantum chip, and here you see actually our latest chip. It's a 22-qubit chip and sits in our labs in Santa Barbara. We use superconducting qubits, and they operate in these devices that you see here to the left, so-called dilution refrigerators. They keep the chips at about 10 millikelvin. And so the little quantum algorithm that I showed you can be put onto the quantum chips. That's what they're made for. And then I can do this protocol and essentially measure m bit strings. Yeah, so I take m samples from this probability distribution. And then next thing is I will try to see with which probabilities should I have seen those samples. And we initially worked together with high-performance computing experts at Intel. It's nicer to play against a red team, not play against yourself. And they managed to push this to 42 qubits. So for 42 qubits, they used the Edison computer from Department of Energy. And with that, they were able to give us the exact probabilities with which you should have seen the bit strings when you measure. But just a few weeks ago, there was a team, collaborators of ours, Damien Steiger and Thomas Hanner from ETH Zurich, who improved this. They pushed it to 45 qubits, booking out this machine here on the picture. This is Cori 2 at the US Lawrence Berkeley National Laboratory. It's one of the top supercomputers in the world. And you had to clean this thing out for a whole day to compute the probabilities that the circuits that I showed you produces. And then you're kind of done. And the task is to show that the samples from this probability distribution that your processor, your quantum processor, produces are close enough to the ideal distributions that you wrote down on paper by defining your quantum algorithm, that no classical machine could produce samples of similar quality. And this chart here is a little bit to illustrate why is this a hard task in the first place. It is a hard task in the first place because it's, I don't know whether you have ever seen this, and sometimes I bring a demo along like a little laser, where if you've seen those laser speckles, these intricate patterns that laser produces. This is probably too weak to do this. And those speckle patterns, they come about because it's a coherent light source. So when it goes through a diffuser, let's say some glass, then you have a lot of different pathways the light can go. And sometimes you have constructive, sometimes you have destructive interference, and that makes these very intricate patterns. Versus an incoherent light source, if you would just have taken an LED and shine against the wall, then you get sort of this washed out pattern. So basically, because we have a very coherent device, you get these speckle patterns, but now in Hilbert space, in qubit space. And therefore, the probability distribution that you will measure from or draw samples from has this very intricate speckle-like shape. And essentially what's shown here is if I have n qubits, I can get as measurements bit strings of length n. So I measure n, 0, so 1. And here in this picture, they are sorted. So the probabilities from the bit string 000 all the way to the bit string 1111. And it's like there's the bits of a very, very fine key, and you need to sort of draw samples according to this very complicated function. Actually, it turns out, however, is that if you were to reorder those probabilities from the smallest to the largest, you see actually there is structure in this probability distribution, and you get this exponential shape, and it's a so-called Porter-Thomas distribution. And it's essentially the distribution you get if you pick randomly in your n-dimensional Hilbert space a state and then ask what are the probabilities to see the different components of this large superposition state that will be distributed according to this probability distribution. And therefore, if you try to be sort of a classical imposter, you say, oh, I can do this with some classical black box, I don't need a quantum computer, then the challenge is, let's say, take a very simple-minded imposter, just the uniform distribution. If you would just uniformly draw some strings here, chances are you will pick them somewhere here from the middle, but you will miss the ones with the high probabilities. But a good sampler should sample more from the high probability point. And therefore, it's a hard task. And actually, complexity theorists will tell you that if you have a classical machine that tries to produce such samples, the cost is exponential in the number of qubits. And therefore, if you push it to about 49 qubits, then even the largest machine will fall over, because you have to maintain 2 to the 49 complex numbers somewhere on the scratch pad. And that is, we still have machines with enough RAM to keep that many complex numbers, but in every step of your computation, these numbers have to talk to each other, and that creates a huge communication bandwidth need that no computer has and will not have. And versus, I skip the rest of the slides. This is essentially to say you can introduce a measure called the cross entropy, which is a figure of merit that says, yes, these samples really come from a certain probability distribution or not. And then you see that the hardware will be able to produce samples of high cross entropy difference, so of high quality, versus no classical machine can give you high quality samples in reasonable time. Okay, so this is quantum supremacy experiment, and to go forward, I wanted to explain you one important notion that when you hear about quantum computers, you should know. And this is the space-time volume of a quantum computation. Essentially, how our bits are organized, we have two-dimensional chips, so they sit there as a little array, think of like a little sort of square lattice, let's say 7 by 7 qubits. And actually a good way to think of qubits, this was mentioned a few times in previous talks, is to think of them or of their state as vectors on a sphere, the so-called Bloch sphere. And then you come in with your gates to manipulate your qubits. And a gate, you can think of it, will rotate those vectors around. And a single qubit gate will just look at one single qubit, rotate it around a certain axis. And the two qubit gates might do this conditioned on the state of another qubit. So you look the qubit to the left and what state it is, and then according to the state, you turn the other qubit by a certain angle, and then at the end of the day, you measure. So in the beginning, we won't have enough qubits to do error correction. And therefore, we can only have space-time volumes, meaning so the two space axes are again 7 by 7, and then the time axis is how many gates I apply to each qubit. And we have very high fidelity gates, so we approach 3/9 fidelity. It's actually required to do a successful supremacy experiment. But there's still a bit of error. And unless you correct it, you have to think of your quantum processor as you have a certain budget of gates you can execute. And then every time you execute a gate, it gets a little bit noisier, so you have to end at a certain time. And so therefore you have a finite space-time volume. But if you look how quantum computing will develop, the fidelity will get higher, and therefore the space-time volumes will get larger. And eventually we have enough qubits to do quantum error correction, and then you can go in the time axis as long as your patience for the result allows you. So therefore, we think that this year we should be able to do the quantum supremacy experiment. Far out there, once we have error-corrected quantum computers, there is a whole candy store of algorithms such as unstructured search, factoring, semi-definite programming that you can run and where there are proven speed-ups. But the big question is in between. Are there, for processors that have passed the supremacy frontier but are not error-corrected yet, can we do useful things with those? And after the Monday talk, many people came up and asked me, so what is the first useful application rather than an exotic benchmark? And it will be what Feynman already identified early on. Feynman's killer application is actually a simulation of other quantum systems. And you might think, oh, this sounds very inbred, but it's actually very important. If you want to make a better battery, better solar cells, better catalysts for the pharmaceutical industry, on and on and on. Whenever you do sort of engineering on a nano level where quantum effects play a role, then today you have no good tool to simulate such systems, but those processes will allow you to do that. And actually just last week, we published a nice breakthrough in this direction, that actually we have quantum simulation algorithms now that are likely to fit into these early space-time volumes that we can support pre-error correction. Okay, so here's the first maybe message to this community, and that is the following. Like, Stuart often points out that a paramecium, a single-cell organism, can do all these amazing things, such as finding a mate, avoiding an obstacle, even do simple learning tasks. And as a roboticist, you have some respect for this. These things are not that easy to program. So what I just told you is that a rather small quantum circuit with just 49 qubits and just 30 to 40 circuit depths, so 30 to 40 gates per qubit, that's already supercomputer level stuff. And there's just plenty of opportunity to tuck such a little circuit away somewhere in living organisms. I'm not saying that the coherence environment is necessarily all there, but the message is there are just many places where you can tuck away a supercomputer grade machinery inside some living system. Okay, so let's play around with these early quantum circuits and see what we can do. And a recent game that I'm playing with my co-workers Edward Farhi, Jeffrey Goldstone, and Samuel Gutman is to do quantum neural networks on these near-term processors. And I've seen earlier some slides for neural networks. These circuits here don't look too different. Again, you can present an input pattern by setting your qubits up, down, so you present a binary input pattern. You push it through your gates, and then you go to one qubit, and you measure the qubit, let's say, in the y direction, and if your qubit points in the plus y direction, then you declare the label to be +1, otherwise it's a -1. So it's a straightforward way to represent a Boolean function, and you can, very similar how you would do it with neural networks, you can define a loss function, which essentially counts how many times are you doing correct or incorrect classification on your training example. And then I told you earlier that you can think of these gates as sort of they rotate the qubits. So instead of weights like in neurons, you have angles in these gates. And essentially by changing these angles, you change the input-output function. And you can now ask questions that a machine learning person would ask. Can I classify something with lower time complexity than a classical network? Do I need less samples? You know, that machine learning people always want to know, how many training samples do I need to train a certain architecture to drop below a certain training error? Yeah, I can also ask, how bad is it if my data is polluted? And there are actually a number of new games to play when you consider quantum neural networks. And for example, the answer, can I get away with a shorter quantum neural network than what I would get away with classically? And the answer is probably yes, and I realize this is a bit of an arm-wavy answer, but you could have sort of, let's say, formalizing factoring as a decision problem. So it's a Boolean function that you may want to choose to learn, and we know that a quantum circuit can do this in polynomial lengths, while the classical neural network or the classical circuit would have to be exponentially long. So there will be such advantages. You can also do things that have no classical analog. I can present multiple examples at the same time in quantum superposition. So what does that do? And finally, the outer loop of this algorithm, which means to set your angles in your gates, the 3 parameters you have for each gate, you could use quantum-enhanced optimization to achieve this learning task. And let me tell you a little bit about this letter. And in previous presentations here at the Science of Consciousness conference, I've told about quantum-enhanced, or spoken about quantum-enhanced optimization and quantum annealing. And I just wanted to give you a late-breaking update where we have been in this. So learning means you have sort of this objective function, and your task is to find a low point. Low point means low training error. A high point means you make a lot of errors. So your task is to find the gate setting, the angle settings that produce a low point. So the way how we formulate this today, and this is a little bit evolved from where we used to be, we use sort of a classical dissipative dynamic. So one that can exchange energy with the environment. Dissipative means if I go down this energy landscape, I have to get rid of energy. I have to give this back to the environment. And that is what a classical, let's say, for example, I could use steepest descent, a gradient descent, and then I come down. But then eventually I will be stuck in a local minimum. And quantum processes can help you with escape from a local minimum. And in the past, we have sort of demonstrated that if your energy landscape has very tall and narrow barriers, quantum tunneling will get through these barriers with higher probability than sort of a thermal classical over the barrier escape. So you have 2 ways to improve on your optimization or escaping a local minimum as compared to classical. But we recently found there's actually much more intricate physics going on, basin of attraction to a different valley, and from there you can hopefully find a lower, better energy point. And it's essentially the physics that you use to understand conduction in a metal. So if you ask, how do electrons make it through a metal? It's a similar physics that is being used here, and it turns out that you can get through this energy landscape at least quadratically faster than what is possible classical. And there's actually a simple case that they considered. It's a so-called impurity band, and this is just the most extreme case. You have sort of 2 local minima, and all the other energy states are sort of high up there. So it's like the landscape is like a flat table. There are 2 holes in it, and you start out in one valley, and you need to find the other one. And then if you analyze this, you find the following. You find that the time so there's this rather complex formula that shows how quantum mechanically these 2 states are coupled. And never mind the whole formula, just look at the exponent here. There's a 2 to the minus n half. And that's rather exciting. You might not immediately find that so exciting, but it's exciting because it's quadratically faster than what's classically possible. Classically, it's an unstructured search problem. If sort of your optimization landscape is flat, there are only 2 local minima, you start in one, I give you no guidance where the other one is, then it will take you essentially linear time. It will take you 2 to the n. For any class, for the best, it's easy to prove, the best classical algorithm will take time steps 2 to the n, while here, using this many-body delocalization physics, you get there quadratically faster and only in 2 to the minus n half steps. And this other point can actually be rather far away. So that's why we are getting more and more convinced that quantum-enhanced optimization in general will do better than what you're classically able to do. Okay, so from here, 2 more lessons. One is that shallow quantum circuits can act as learners. To be honest, the exact properties are not yet known. This is sort of a new area of study. But we have good reason to hope that there are advantages in time complexity, in robustness to label noise, and sample complexity. And another observation, this is more sort of targeted to my colleagues, the ones that were earlier mentioned by Joscha, that do traditional machine learning. They will say, come on, Hartmut, how many qubits do you have? Like 50. And you go circuit depths of 50, that's just tiny. We use neural networks that have literally 1 billion parameters to tweak, and there are millions of input parameters. So what can you do with your little quantum neural net? But of course, what we can always do is we can just replace the last layers in a deep neural net by a quantum neural net. And if there are advantages to a quantum neural network, we can have such a hybrid architecture. That's why I like to show you sort of the quantum neural network sitting in a single cell. I could actually think of the quantum layers are just sort of the executive decision-making level for a much larger neural network, which in part may be classical. So that's a possible scenario. Okay, so I come to the last part of my talk, and the nice thing about this conference is it sort of encourages you to go to places where you cannot say sort of just hard, crisp things like we typically strive for in engineering. And that's about subjective experience in machine learning. And so not too long ago, I went through an episode that reminded me of the stark difference between human learning and machine learning. Actually, I have a little boy, and I try to teach him how to ride a bike. So we went out in the street, I sort of helped him up, stay on his little bike, and didn't go too well, And then me, bad dad, I said, hey, come on, you're a little clumsy. Shit, I shouldn't have said this. And he was devastated, like, really, Dad, I'm clumsy. Okay, so the next day we went out, like I held him on his bike, and somehow he got it, So he zoomed down the street, and he was just so happy, like every single fiber of his being, like, yeah, I got that. And I sort of, as a machine learning person, I was just, yeah, that's obvious. We all know this firsthand, that there's essentially a congruence between learning success and a pleasant feeling. And if you subscribe to materialist worldview, let's say something that Roger put forth, then you can get around from assuming that there must be certain states of matter or certain evolutions of states of matter that feel better than others. Yet, nor physics nor computer science has any model, barring sort of ones that we can't really implement. We don't really have a model of what constitutes a state of matter that feels pleasant. And I would even argue that, not knowing this, but I think we can make some arguments why I think a machine learner is unlikely to have this congruence between success in pattern classification and a pleasant feeling. And the reason is as follows. Even though the overall situation, let's say if I were to program a robot to ride a bike, then the overall situation is not symmetric. There are right actions and wrong actions. As I know, in these times of fake news, we seem to forget that there is objective right and wrong often. You either fall over with your bike or you don't. So there is an asymmetry there. But then, if you look closer how machine learning people implement it, they look at the loss function, they look, do I go down, or did I do this last pattern right or wrong, and then I have a plus or minus, I get a positive signal or a negative signal, or I get a larger loss or smaller loss. But at the end of the day, let's say, for example, setting the sign differently is just setting a 1 instead of a 0 somewhere. And it's just hard to argue that if, let's say, having the 1 over here, as opposed to shifting it over a few memory cells, that if that state, let's say, feels good, that suddenly this other state here feels bad, or vice versa. It's just too similar. And if you go even lower and look how the zeros and ones are implemented, let's say like in a flip-flop circuit, it's just symmetrical again. And to be even more extreme, I could have just changed the labels of, let's say, the +1 and -1 in my learner and put a long cable to another little system that all it will do is change the sign again. Then this whole initial piece would operate, but just inversely. So the pleasant and unpleasant feelings should just switch. So I think it is implausible. And in a way, if you think about it, if you don't have a model for what constitutes a pleasant or unpleasant state, it would be miraculous if you would have implement our learning routine such that this coincides, or you have this congruence for a machine learner as well. I would rather think it would, if anything, it would feel confused. So I took time to doodle around a little bit. I thought, okay, can we, with our new quantum computer, we have now quite some mastery to a high degree of fidelity to produce states of matter and to go through evolutions of state of matter. Could we possibly organize it such that we build an AI Skinner box? We make it go through a pleasant experience, and then we want the circuit to ask for more. But it didn't get very far. Let's say you start with a decision where with a certain probability you do something that's pleasant, and with a certain probability 1 minus p, you do something that's unpleasant. How would you proceed from here if you would assume that you have some measurement device that can tell you how happy you were when you went through this process? Then it's rather straightforward. You can go back and you update your p so that you go more to the happy branch. But in the absence of somebody who makes a suggestion how to measure this happy operator, then we can't really do it. I have no idea. But the last slides, I want to sort of offer up a proposal. Now, so again, we stay in the materialist worldview and say that pleasant states or pleasantness or unpleasantness must be associated with a state of matter or its evolution. And what I would like to explore is the notion that relaxing to a stable state is associated with a pleasant feeling, and evolving to an excited state is associated with anxiety. And it's maybe telling that physicists already use these psychological notions. There was no need for it, really, to call it such. And essentially what you would find is if you adopt this notion, there is this interesting idea or observation that physical and psychological perspectives become congruent. Yeah, so the physicist would say the system evolves this way because it minimizes Gibbs free energy, but a psychologist would say, no, it does this because it feels pleasant. And there's, of course, also logical consistency. An organism that has pleasure in doing things that destabilize it, this organism will not be around for very long. And there are also engineering advantages to mapping patterns or, let's say, positive learning results to stable states. We already saw that now you can take advantage of quantum tunneling. And also, if you use stable states in a deliberate way, you find that this helps you stabilizing percepts and behavior patterns in the presence of noisy sensor readings. Okay, and the very final thing, with this notion that relaxing to a stable state feels pleasant, you could think of psychedelics as literally a catalyst for the state of mind. Yeah? Because again, if you're a materialist, you must be in some state of mind, and what happens if this is catalyzed somehow and goes through a typical chemical reaction. So we think of psychedelics as nothing more than this, help to catalyze a reaction. And then we can ask the question, what would happen if you're in a state of mind, a catalyst comes in, and you go, let's say, through a tunneling transition. That's sort of an interesting thing to think through. And to me, it explains one piece. I sort of, for about 10 years, I'm working with an Amazonian entheogen called ayahuasca. And sort of every time, even though I do it for 10 years, it's sort of the same thing. The onset of the experience is very scary. You're anxiety-ridden, and once you come out on the other side, this feels extremely peaceful. And maybe it's just me, a scaredy cat, but looking at my fellow folks who go through these experiences as well, it seems to be similar to everyone. So this notion that destabilizing is associated with anxiety, stabilizing with pleasantness would sort of fit this here too. And then you also have this nice situation that you have sort of this double description. Finding this lower state here. In computer science, or computer scientists would say, you found a solution to a problem. But in physiological terms, you may say you relaxed, or this relaxation corresponded to finding a more stable homeostatic equilibrium. So kind of healing and problem solving sort of goes together here in this model. Okay, I think I outrun my time. So this is the team in Venice Beach and Santa Barbara, the software and hardware teams for the Quantum AI group. And thank you.
Thank you very much. Right. Well, we're a tiny, tiny bit behind time, but that's only because we started 10 minutes late. And I'm obviously in desperate trouble with Roger for allowing it to go late, but I was trying to explain that this is San Diego, and we're very relaxed and kind of, yeah. So I hope that's okay. So if we get our speakers up on stage, can you want to sit up on stage? And we'll just answer a few questions that are burning to you. Do we have a couple of roaming mics, do we? And why don't I take a couple of questions while we're assembling people, and I'll try and remember them, and then I'll be able to speak them back, and so on. So the gentleman in the black, why don't you ask the question of me, and then I will deal with it once we've got all our speakers here. Yes. Right. Okay, got that one. Another one? Gentleman in the white.
Yes. I found it interesting with Neven's presentation. I've thought about this a long time myself, the difference between pleasure and pain. It occurs to me, and I'd like you to comment, that it's somewhat like dissonance. In other words, pain. And pleasure is more like consonance. It's almost
Okay,
like...
so a musical analogy.
Like a musical analogy, indeed.
Okay, and one more question, I'll stack up, and then I'll start divvying them out. So musical analogy. Gentlemen, yeah? Yeah?
Yeah, this is a question for Dr. Penrose. Do you think that the laws of the universe is the consciousness or awareness of the universe, taking the fact that every space and time, moment of time in universe is aware of these laws?
Itself? No. I mean, the universe as a whole, not in my opinion, I mean, you could imagine such a thing, but in my opinion, consciousness comes about when the proto-consciousness is organized, orchestrated in a way, in relation to the first question, which I don't have any clear idea about, I'm afraid. So I don't think the universe as a whole is conscious. It would need to...
Can I repeat the question?
Sorry?
I don't think it answered when he got the question, because the question got changed.
Oh, I see. The question's changed.
My question is that since the universe is aware of the laws, every moment of time and space knows the laws of conservation are to be true, does that mean its awareness, let's forget the consciousness, is the universe aware of its laws constitute the awareness of the universe?
Not in my terminology. I mean, the universe as a whole is not, in my view, aware of anything. It's not, that's, aware is just an aspect of consciousness, in my view. I mean, it's not the whole of consciousness, but it's some aspect of it. So, no, I mean, it would have to, the view is that you have to have this reduction, spontaneous reduction, and the spontaneous reduction is just an element of proto-consciousness. It's not the universe as a whole, it happens in certain places. So I can't see that the answer to the question is yes, in my view.
So the second question was about basically to what extent is pleasure and pain similar to music or some sort of thing like that. So why don't I give that to Hartmut and then you can...
Yeah, I felt I went already out on a limb proposing that relaxing to a stable state is, feels pleasant and going to an excited state is unpleasant. It just struck me that this fits together with a number of observations or logical constraints. Sort of pushing it beyond this, it would be, I don't know, maybe somebody comes up with sort of a measurement protocol, how we could assess. I mean, obviously it cannot be such a subtle phenomenon in the human nervous system, and there's of course all sorts of studies what happens when you eat a cookie, but sort of breaking it down to at what are the systems that really correlate with a pleasant sensation, that we're still far from that.
I think pleasure is a learning signal. It's created whenever you feel a need, and it's proportional to the amount of need fulfillment that you do per unit of time. With respect to music, the pleasure that's generated from music has many possible dimensions. One of them is aesthetic. You have a certain structure discovery that possibly piggybacks on some of the functionality that we have for learning language. Then there are physiological parameters that might be elicited by music, that you entrain your physiological rhythms and your brain patterns with the music, which itself can be intrinsically pleasant. Then there are social connotations that go with music, narrative connotation and so on. They can fulfill many, many different needs, and this means that music can be intrinsically pleasant if you are susceptible to one of those needs.
This question is regarding neural networks. So we have been talking about deep neural networks. So as we understand that it is a basic computing unit, and we also talked in morning about microtubules. So can microtubules be considered as basic computing unit, which can which can, the quantum effect can be implemented using it? And the third part is that when we talk about the concepts, biologically these are electrical spikes. How do concepts translate to these electrical spikes?
So I think the question is a neuron a computing unit, and how does a neuron represent concepts?
That's right.
Gosh, is there anyone else up here who'd like to answer that question? We don't have any neurologists up here, remember? Who would like to? Joscha, come on, you can do that one.
I don't think that concepts are represented by individual neurons. They are represented by ensembles of neurons. And I suspect, and it is not a thing that is completely consensus yet, because there are a multitude of theories on how that works, that concepts form a map that is something like the address space of your sensory motor scripts, of the things that produce your mental representations. And concepts are synchronized between speakers through language, which is why we can use statistical analysis of language to do machine translation. These machine translations work only on conceptual structures, nothing below this. They cannot imagine what the concept means. The concept is basically what anchors different linguistic symbols that are synonyms on some part of a landscape. And this landscape is a map that is produced and held stable by a multitude of different neurons that are working together and forming circuits and oscillators. Does this answer your question?
Excellent. Middle back there.
I have another question for you. So in your model, what do you think the difference between consciousness and self-consciousness, or let's say self-awareness in your model? What is the
What's the difference between awareness?
And
so who are you asking the question to?
I don't remember, but the middle...
Joscha, right,
Joscha,
okay.
Yeah, thanks.
So is self-awareness the same as awareness of other things?
Yeah, let's say, do you have the awareness or consciousness about pain, and the awareness that you are the one that has this pain, no? So,
okay.
I think when you meditate, you can discover that your awareness of yourself can be redirected on the awareness of something else. So for instance, you might identify as a perspective being with the universe itself if you lose the connection or dissociate it to your self-concept. Which means to identify, for instance, as a human being or as a social person or as somebody who wants something and so on is somewhat arbitrary. It's a trick that the mind uses to make a particular kind of model and regulate that model. And you can change that model into becoming aware of that you are the universe. And you have the illusion that there's a cosmic consciousness because suddenly your representation of the universe gets unified with what you think is your perspectivity on it. But this is a mental state. There is a difference between this perspective self and the awareness of having a consciousness, of having conscious access. And the awareness of consciousness doesn't need to have content. It's the awareness of the fact that or a model of the fact that there is a process that accesses your own models.
The question was is self-awareness the same as awareness of the world? Did I have that right? I mean, the same kind of thing, I would say, but self-aware, I mean, I'm just going to make a stupid, obvious comment. Self-awareness is awareness of oneself, and awareness of the world is awareness of the world. They're just different. The awareness is the same, but they're different things it's aware of.
Yep. I'll give that to you. So next question. Do we have one for Hartmut? Hartmut? Okay.
I was confused by your observation 3, where you said that it would be worthwhile to replace the top layers of a neural network with a quantum computer. I would have expected the exact opposite. For example, when we do transfer learning, we remove the top layers of a neural network and replace it with an SVM, for example. Okay? So why is my intuition wrong? Why wouldn't it be that you would want the quantum computer to discover better features, for example?
For example, if we were to find, let's say what we have done like little numerical tests for simulated quantum neural networks. And then we found, for example, that we could learn something like subset parity to a much larger number of inputs than a classical neural net. Essentially, the classical neural net would have to be larger to do the same thing. It would have more parameters, and therefore it takes a longer time to learn. So if you were to find, let's say, a mapping from 50 input units to just one output unit for certain types of learning tasks works much better on a quantum neural network. For better meaning, for example, lower sample complexity, you need less training samples, then you can easily use this in a much bigger context by letting the lower level tasks, such as feature extraction, be done by the early layers of your neural network. I'm not saying this is the only way to do it, but this would be a very straightforward way that, let's say, often deep neural networks, even though they might have thousands of output units, they are often, if you use something like logistic regression, essentially each output neuron fights for itself, and there are sort of these funnels that end in single neurons on the output layer. So it's just a very straightforward way to use a quantum neural network here and now, as soon as we discover, even on a 50 input quantum neural net, some advantages.
Okay, so your observation was basically about efficiency and speed rather than better features, right? That particular observation. Yeah,
in the moment I'm just after efficiency and speed, yeah.
Okay, thank you. Another question for Roger, maybe? Okay, gentleman on the blue, one in from the green, and then maybe you can negotiate between you as to whether you've got the same question or a different question.
Okay. My question was for Roger. Roger, I don't understand what your post-collapse wave function looks like. If you look at the spontaneous collapse theories developed by Philip Pearl and Girardi, Remedi and Weber and so forth, if you have a particle which initially starts out, it's confined to one dimension of space, and it initially starts out in a superposition of two Gaussians, where those Gaussians are located in separate places along the dimension of space, then the post-collapse wave function is still a superposition of two Gaussians. One is just raised and the other is lowered. And there are technical reasons for why they have to settle for this. But what it means is that the post-collapse wave function is still always a superposition. In the literature, that's called the tails problem. So I'm wondering what the post-collapse wave function looks like on your theory, because it looks to me that if your post-collapse wave functions also have tails, then you can never remove superpositions of space-time curvature.
I don't think I understood the question. I mean, you have these ideas of Joscha Aharonov involve pre-selection and post-selection, and you can get cases where you have rather extraordinary things happening. Well, they very rarely occur, but they seem to be rather strange. I'm not sure if that's what you're talking about, and I didn't quite see, I'm afraid I didn't understand the point at the end.
Okay, so I know you, and I know your physics is fairly thorough, so that's a discussion over a cup of coffee. Thank you very much for that one. That's a gentleman in the green in the middle. Oh, sorry. We've got a man with the...
This is a question partly for Roger and partly for everyone else, and I'll set it in context. The question is very simple. Why do you assume that there is only classical physics and quantum physics, and everything you have to do with computation, computationalism, or any other computer calculations you're using is only going to be looking at quantum theory and quantum models? That's the question. Now I set it in context. In the human physiology, everything happens from criticality. Everything in human regulation, which ultimately means the human mind, happens from complexity. And complexity means instability, and the physics of instability, which is critical instabilities, has nothing to do with either classical physics or quantum physics. So why do you limit yourselves to quantum physics?
Well, I'm going to answer a little bit of that question.
Was that a question?
Okay. So I think that what you're saying is that people on the panel, including me, are only talking about classical or quantum physics, and I think that that's wrong. I think what Roger is saying is that classical and quantum physics are insufficient, right? That something appears to be going on in our heads that would require a modification to quantum physics as we know it at the moment, which is not quantum physics as we know it at the moment. So we're trying to add an additional feature.
Yeah, I sort of agree there. Yes, I mean, the view I have is that classical physics and quantum physics are both approximations to something that we don't know yet. We get some idea of what it's like, but we need to have a better theory than either one or the other. It's true that in many circumstances you can treat it according to quantum physics or according to classical physics, because the other part doesn't play much of a role. But yes, there's something more, as James was just saying, and the something more would have as limiting cases our current view of quantum mechanics or our current view of classical general relativity. And so one has a more inclusive theory. It's not that you have one or the other. You have the bigger theory, which may specialize in some circumstances to look like quantum physics, or in other circumstances to look like classical physics.
I think the other two, it'd be interesting to see what
I think that it's a very interesting division between us. It's completely correct to say that you are trying to go beyond current physics. You try to make an extension to physics, which is very bold because we don't have data in this particular area. It's more conceptual. We don't know what that is going to be yet. Physics at the moment assumes that the world is made from quantum fields that evolve to some kind of Hamiltonian, or another mathematical formalism that comes down to something that is mathematically equivalent but written down in a different way. And it could be that we change that, but we don't know about this. And for us, the question is what kind of computation is facilitated in this universe or outside of this universe, and what kind of computation do we need to build the equivalent of minds? Roger thinks we need computation that goes beyond the computation that is known in physics. I think the classical computation is probably sufficient. You think that classical computation is probably sufficient, but it's going to be much faster with quantum computation, right?
Why don't you hand the microphone to Hartmut and he can answer that question.
So maybe first I want to make a bit of an upbeat observation, in the sense that what we observe is that quantum information has given fields of physics that previously were not talking to each other much a common language. So suddenly people who wonder about the information paradox of black holes and wonder what happens if you throw a qubit into a black hole which is entangled with another qubit that's outside of the event horizon, or condensed matter physicists or quantum biology folks, they can all look at each other's equations now and understand to some degree what the other is doing. So I think that bodes very well for the next 10 years, seeing interesting fusions of areas of physics. But of course, the fundamental part of your question is more, this may be a bad excuse, but we just take baby steps. Quantum physics is what I have now, what I somewhat understand, and we can build machines based on this theory. I'm not by any means saying this is the end of it, and I'm, of course, a history of science would suggest that in probably 50 years we will talk about maybe David Deutsch's new constructor theory or completely other forms of physical theory. I don't know, but it's likely.
Gentleman in the hat, who's
Yes,
obviously got a burning
just
question.
Final comment.
Hello.
Instability physics is completely non-computational.
Okay, thank you. Gentleman in the hat.
Hi. I know that most of us here and most of the discussion around artificial intelligence, seeing as we are human beings, the model that we have in mind, the Holy Grail, is to replicate the human mind. But seeing as there are so many different forms of intelligence on this planet, is there a benefit to the development of artificial intelligence looking at non-human forms of animal problem solving and other forms of intelligence?
So this would be squirrels and crows and dolphins and other
ants
things.
And bees. And are there situations where non-human forms of intelligence may be able to complete tasks better than a human-based AI?
You got the microphone?
The main form of artificial intelligence will not be robots that are existing on the same level of us. The main form of AI will be organizations. It will be corporations, nation states, universities, whatever needs compute to make sense of what it's doing. And we will be living inside of AI largely, not next to it. It's not going to be robots that compete with us for resources. It's going to be stuff where we are going to be mostly the microbiome. Of course, there's also going to be intelligent artifacts, but it makes probably more sense to imagine robots as the extremities of future AI. In this sense, we should not expect AI to be very similar to human AI. Personally, I'm interested in building humanoid AI because I want to understand how we work. I'm also interested for the same reason in animal-like AI, because I'm interested in how minds work in general. But in practice, if we are able to build sentient machines, they are going to be organizational things mostly.
And Roger, we've talked about whether squirrels or dogs were conscious or intelligent. You know.
Yes. Well, I think the way I look at this question is that the reason that AI seems to be trying to compete is perhaps the wrong word with human intelligence is because that's what it's trying to do. I mean, it's trying to play chess or Go or whatever it happens to be, or do things that human beings do, and maybe sometimes try to do them better than humans do it. And we're not so interested in trying to do machines that do things better than squirrels. But I don't see why you shouldn't study that. It's just, you wouldn't get so much money, I suppose, for studying AI for squirrels. But it seems to me it's just this is the way it's driving, and that's why AI is aimed. I don't think it's at all like what humans, the way we think or what we do. I think what we think and what we do is much more like what squirrels do than what AI does. But that isn't perhaps the question.
And Hartmut, when your quantum AI machines or your quantum computing machines grow up and they become very powerful, will they look anything like a human being or a squirrel or a dog or nothing like them?
First of this question, actually, when I wrote my PhD on autonomous mobile robots, the strategies we use to have them navigate through our institute and find back, let's say, the power station. That was very much modeled after how ants or rats navigate, or simpler systems, simpler animals. That was very fashionable at the time, and I'm still a big fan of looking sort of at, I think, for example, the intelligence of a single cell is way underappreciated. I think if you look in evolutionary periods, I think a single cell is probably the most optimized machinery, and I would like us to think more what amazing feats, or what it would take to replicate the amazing feats of a single cell. Big fan of this. In terms of quantum AI, I think I made in my talks there's a case that I'm convinced that the most I think creativity can be well described by, or formalized by, finding a low point in an objective landscape that expresses an optimization landscape. And quantum enhanced optimization will be better in finding those low-lying minima, and hence will be the most creative system we know to build to date. So I have no doubt about that.
One important point is maybe think about the difference between a dog and a human. What is that difference between a dog mind and a human mind? One of the obvious differences is given by the affordances of the dog. The dog doesn't have hands. It smells, has much better smell than humans. And this means that the world presents itself very different to a dog. The next thing, a dog has different needs. The social needs and the cognitive needs of a dog are very different. As a result, it's going to pay attention to very different things, and it means it learns very different things, because you only learn things that give you reward signals, and you only pay attention to those things that capture your attention because you have a need that is related to them. And then the largest and maybe most important difference is that our development is much, much slower, and our brain is slightly larger than the one of a dog, which means during our adolescence, during the training phase of our brain, we see vastly more training data than the dog's brain. So we get to much better abstraction than a dog can possibly get to.
Thank you. Yep. So, unless, do you have one more last thing to say on that point?
Me?
Well, I think we're at time. So is there one more burning question out there that someone feels must be asked or answered today? A really bad, the gentleman right at the back there that hasn't spoken so far.
I have a question for János, and I'm wondering if he feels a current modern digital computer could ever become conscious running a software program.
Oh, well, that's the topic, isn't it?
And if not, what hardware would be required to make a computer conscious?
What hardware would we need, well, to make a computer conscious? So Roger Penrose would say...
Well, you need to take advantage of the quantum state reduction. I mean, it's not a question of using artificial intelligence in the way we use it now. You need to have something which harnessed, I mean, it was in relation to, I think it was the first or the second question, which I didn't have a clear answer to. Namely, you would have to, on my view, have a way of taking advantage of what's going on in quantum state reduction. See, at the moment, it's very hard even to see the effect at all in an experiment. So we're way off it. But without doing that, in my view, we don't have consciousness at all. So in my view, none of the devices, artificially intelligent devices, computer-driven devices, have any consciousness at all. Unlike us, something is going on in our brains which involves, on the view I hold, the reduction of the quantum state, and that being correlated, orchestrated over large areas of the brain, and that would, on this view, enact consciousness. But we're so far off doing that at the moment. We don't even know from physical experiments that this process that I'm talking about actually exists. We know that something must happen in the reduction of the quantum state, but we don't know exactly what's happening.
And Joscha, do you think a computer could just do it?
Yes.
You only got like a one-sentence answer here.
Roughly a year ago, I taught a class at MIT about the future of AI, and I took a small survey in that class on what kind of hardware do we need to build a mind that is capable of human performance and consciousness and so on. I think most of us felt that consciousness is going to be naturally emerging as soon as the system starts to model its own attention properly. And the capacity for doing that, the majority of the class was quite optimistic. We thought we can probably run a person on 200 gigabytes if we only knew how. We don't know how. We are pretty optimistic with respect to this, but we have some reason to believe that these numbers might already be sufficient. We had a couple students that thought we need petabytes, and we had one student that we thought we need exabytes, but they were the outliers.
So, Roger, a quantum gravity computer. Joscha, a big enough computer. And I think, are you undecided at the moment? I think.
No, but you're asking the wrong person. I'm personally, my view on this is more the panpsychist view, is that essentially I think consciousness is associated with elementals of physics, and we should more think about it like mass or spin or possibly state reduction, as Roger suggests. In that sense, consciousness pervasive. It's already in a grain of salt or sand, I would say. There is some proto-conscious present.
So, sort of the wrong question. You don't know machine would do it. The universe sort of kind of is.
May I just make a slight objection to the term quantum gravity computer?
Yes, of course.
Because first of all, it's not quantum gravity, because the term quantum gravity means the correct application of, the application of what we regard as current quantum mechanics to gravitation theory. Whereas this is almost the opposite. It's gravitational quantum mechanics. I don't know how you say that.
I shouldn't have
sorry.
baited you in that way.
There should be a good term for it.
Yeah, we need a good term for a relativistic quantum computer or a modified quantum computer.
Think about it.
Thank you, everybody. That's the end.